Today we are going to look at section 6.2. So we are going to continue looking at the sum and difference formulas for cosines, sines, and tangents. So when they're asking for us to find the exact value, notice that the problem that they're giving us is in terms of tangent. So we should be thinking about the sum or difference formulas for tangent. Notice that in the numerator, I see that two tangents are being subtracted. So that means that we want to follow the formula for the difference of tangents. So notice that in this problem, our alpha is going to be this 3 pi over 10, and our beta is going to be pi over 20. So I'm going to be able to condense this down to the tangent of 3 pi over 10 minus pi over 20. Because these fractions have different denominators, I need to have a common denominator. So between 10 and 20, 20 is going to be that denominator, which means the first fraction I have to multiply the top and the bottom by 2. So that would give us 6 pi over 20. That then allows us to subtract. If I subtract 6 pi minus pi, gives us 5 pi, and that's still all over that common denominator of 20. And notice that 5 and 20 are able to simplify down, so this turns into the tangent of pi over 4. So now that I see that really we are dealing with an angle that is within our unit circle, we can either use our unit circle or sketch a quick picture. Remember, pi over 4 is in the first quadrant because that's a 45-degree reference angle. The two legs are congruent. They're both 1. They'll be positive because we're in the first quadrant. So notice that even though I have the hypotenuse, it doesn't really matter because tangent is opposite over adjacent. Notice that the two legs, 1 over 1, tells us that our answer is 1. Let's look at verifying. So if it wants us to verify this identity, that sine of alpha plus beta plus sine of alpha minus beta equals 2 times sine of alpha times cosine of beta. Remember, we have to pick the more complicated side. And so for me, that is going to be the left side. Notice that on the left side, we have both the sum as well as the difference formulas for sine. So if we remember, it's these formulas right here. So I'm going to substitute in each of those. So I'm going to start with the sine of alpha plus beta. That'll be this first formula. So that's the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. Now I'm going to do plus, and now in parentheses, I'm going to put the second term. So notice that sine of alpha minus beta is this second definition, where it's the sine of alpha cosine of beta minus cosine of alpha sine of beta. All right. I put it in parentheses. Granted, the sign in front is addition, so that's really not going to change anything. So if you want, you don't have to put the parentheses. If that was a subtraction sign, you would want the parentheses so you distribute the negative correctly. All right, notice that we can start combining like terms. I see sine of alpha cosine of beta, not once, but twice. Both of them are positive, so that means I have 2 sine of alpha cosine of beta. Notice that my cosine of alpha cosine of alpha sine of beta, and then over here, cosine of alpha sine of beta, but that one's negative. Well, a positive and a negative, those cancel out. Notice that what I have is what I was asking for. I have the right-hand side, so I'm done. If I want us to verify this, sine of alpha plus beta all over cosine of alpha cosine of beta equals tangent of alpha plus tangent of beta. Once again, we have to pick the more complicated side. I think that the left looks a little bit more complicated because it has the sum of 2 angles as well as a fraction. So I'm going to start with the left. All right, so if we just look at the numerator, once again, we have that definition for what that sum is. So that's going to be the sine of alpha cosine of beta plus cosine of alpha sine of beta. That's still all over our denominator. All right, because our goal is to turn this into two separate terms, we can use our strategy of breaking apart the fraction. So that turns into the sine of alpha cosine of beta all over cosine of alpha cosine of beta, plus, now the second term in the numerator, cosine of alpha sine of beta, all over that same denominator, cosine of alpha cosine of beta. Hopefully we noticed that with these two fractions that in this case, the cosine of betas are going to cancel, and over here, the cosines of alpha are going to cancel. So because that then gives us the sine of alpha over the cosine of alpha, plus the sine of beta over the cosine of beta. Well, both of these are sine over cosine. We'll notice that sine over cosine is the quotient identity, which gives us then tangent. Now notice that the first one is dealing with alpha, plus, and then the second one is dealing with beta. And that's what I wanted, so I'm done. All right, here's the last type of problem. It says, suppose that the sine of alpha equals 4 over 5 for a quadrant 2 angle alpha, and the sine of beta equals 1/2 for a quadrant 1 angle angle beta. Find the exact value of the following. Cosine of alpha plus beta. We're going to use this and we're going to do the cosine, we're going to do the sine, and we're also going to do the tangent. So we're using this exact same thing. We're going to do it 3 times. All right. So if they're asking for us to find the cosine of alpha plus beta, means we want to use this definition right here. So I know that I want the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. Okay, based off of the information that they've given us, they're giving us the sine of alpha. So I can technically already plug that in to one part of this. And they're also giving us the the sine of beta. So that's this part. So I have half of this already figured out, but notice that I don't have any information on the cosine. Well, this is where sketching a picture is going to help us. So going back to this first piece of information, sine of alpha is in the second quadrant. So I know that I'm going to have a picture where in the second quadrant, I want to have a triangle where alpha is in it, and sine is opposite over hypotenuse. Hopefully we notice that this is a triple. It is really a 3, 4, 5 family. So 3 is going to go on the missing side. But because we're in the second quadrant, notice that moving to the left, that has to be negative. So technically then I have enough information to substitute in for the cosine. I now know that it's negative 3 over 5. In the second part, it says the sine of beta is in the first quadrant. So I can sketch a triangle in the first quadrant. That angle is beta. And once again, sine is opposite over hypotenuse. I want to find the other side. Well, hopefully we notice that if we have a 1 and we have the hypotenuse is 2, that this is technically a special right triangle. If you didn't, you could do Pythagorean theorem to find out that that missing side was the square root of 3. In the first quadrant, everything's positive. So now I have enough information to find the cosine of beta adjacent over hypotenuse makes that the square root of 3 over 2. So now all I have to do is multiply the fractions and combine. So negative 3 times the square root of 3 is negative 3 root 3, and that would be all over 10, because 5 times 2, minus 4 times 1 is 4, 5 times 2 is 10. Well, technically you could reduce down that fraction because I want to combine the fractions. Notice that they already have that common denominator, so I'm going to leave it as a 10. And so negative 3 root 3 minus 4 goes in the numerator, all over 10. This would be my answer. All right, so using the same information, sine of alpha is 4 over 5 in the second quadrant. Sine of beta is 1/2 in the first quadrant. Now I want to find the sine of alpha plus beta. So if we use our definition, remember that we can say it's the sine of alpha times cosine of beta plus cosine of alpha times sine of beta. And it's the exact same terms as the first one, so that means we still get to use that same sketch. All right, so sine of alpha cosine of beta plus cosine of alpha sine of beta. So notice that sine of alpha was given to us in the original problem. That was 4/5. And then the sine of beta was also given to us in the original problem as a half. But with the sketch, we know that the cosine of beta is adjacent over hypotenuse, so square root of 3 over 2. And I know based off of the sketch that the cosine of alpha, adjacent over hypotenuse, is negative 3 over 5. So then just like the last problem, I can multiply my fractions straight across. That would turn into 4 root 3 over 10 plus, then we'll have a negative 3 over 10. And then they have the same denominator, so I get to combine it as 1. And so I've got 4 root 3 minus 3 on the top all over 10. And that would be my answer. And then finally, same information, but notice that this last problem now, I want us to find the exact value for the tangent of alpha plus beta. So we know that this is our definition for tangent. We are going to add the two terms on the top and then all over 1 minus then the product of those two terms. And because it's, once again, the exact same information, sine of alpha is 4/5, sine of beta is 1/2, we're still using that same sketch. All right, so if I know that tangent of alpha plus tangent of beta goes on the top, all over 1 minus tangent of alpha times tangent of beta, I'm going to look at my picture. We'll start with the alpha, so the second quadrant. We know that tangent is opposite over adjacent, so that's going to turn into 4 over negative 3. That means that it's going to be not once, but it's going to be twice. All right, now I can go over to the first triangle and I want the tangent of beta. Once again, tangent is opposite over adjacent, so 1 over the square root of 3. That's going to rationalize into the square root of 3 over 3. All right, so notice that I've got a complex fraction here because I got fractions inside of fractions. But in the numerator, I technically have the same denominator. I can move that negative on the top. And so really, we've got negative 4 plus the square root of 3 all over 3. In my denominator, we'll have 1 minus, and then if I multiply fractions straight across, we'll have a negative, but then it'll be 4 root 3 over 9. Okay, I would like us to get rid of the fractions within a fraction, which means that I need to find a common denominator. So between 3 and 9, hopefully we're okay with 9 being that common denominator. I'm going to multiply both the top and the bottom by 9. So I'm going to take this negative 4 plus the square root of 3 over 3. I'm going to multiply that by 9. In the denominator, this 1 technically minus a negative, turn that into an addition problem. I'm going to take this and also multiply that whole denominator by 9. All right, that should clear away the fractions within the entire fraction. So in the numerator, because I'm multiplying by 9, but I'm essentially dividing by 3, that would give us then 3 being multiplied by negative 4 plus the square root of 3. In my denominator, if I distribute that 9, 1 times 9 is 9, plus, and then if I have 9 and I'm dividing by 9, that will just leave you with the numerator. So lastly, because I've gotten rid of all the fractions, I'm just going to distribute the numerator. That gives us a negative 12 plus 3 root 3 on the top, and that's still over 9 plus 4 root 3 on the bottom. And I'm going to let us stop there. So at least I've gotten rid of all the fractions. It's okay that I have a radical in the denominator in this particular case. So that's us, once again, using sum and difference formulas for cosines, sines, and tangents. This is what I'd like you to do for homework, page 605, numbers 25 through 35 odd, and then 57 and 58.